Go ahead and ask.
So on Sunday, we're having the midterm, and you're doing that because we need extra time. But then why can't you just have an extra class on a Sunday and make the test Monday? Because on Sunday, you're going to record it. So if people miss it, you just put it on Blackboard. And also, people have work on Sunday and Saturday, so it could add more stress to their life.
Okay, guys, we can then probably do it on Monday. That's also fine, but I have not received any complaints about like the exam date. If I receive a lot of like feedbacks that you guys cannot do it on Sunday, because I mean, if you cannot, if I have a few requests that they cannot write the exam on Sunday, then we can reschedule for those students and still have the exam on Sunday. But this is something that we will clarify later. So today, let me now start today's class. But just read the class, read everything what I write in the blue Word documents, understand them in details, and also read the class slides and do some homeworks, and you should be fine. I have taught this class multiple times, and from the experience, students are doing fine because they are working hard. Okay. So today I will talk about hypothesis testing. Everything starts by, first of all, guys, do you hear me well, or should I don't know what to do, but let me know if you hear me.
We hear you.
We hear you.
Very nice. So if you have any questions, please stop me, but also note that I will give you more details about the midterm, and it will be like prepared for the midterm. So and also today, right after class, I will be here like about 10-15 minutes, and we can discuss stuff there as well. So everything starts by what? Specifying the hypothesis, right? About the true population parameter. We during the last class we talked about one of the population parameters, specifically the population mean, right? That we denoted by so the population mean is expectation of X or expectation of Y, whatever is your random variable, right? And we denoted it by mu of Y, right? Why do we need hypothesis tests at all? Because we don't know mu. We don't know the true population mean, so that's not known. That's not known because, as we said last time, to know this, what do you need? You need the information. So the details are in the last class, but let me just repeat a few things. To know mu of Y, you need to have the information about all the observations in your population of size n. That's how usually we denote population size, and this is usually a very large number. It's like very costly to get the information about everybody or every population or every observation in the population. So what do you do then? So what you can do is that you can take a sample out of the population. Of course, there are certain requirements for sample to be good. The requirements for sample to be good are sample to be good are first, sample should be random. and it should be representative. Okay, it's like sample size n. If sample size n is, let's say, about, let's say, 30–40% of the population, then you are fine, right? But sometimes you don't even have that much information. You take a sample and you can calculate what? A sample analog of the population parameter. But the sample analog should be good. Since you read the class slides and you probably been during the last class and you read the class notes, what are the requirements this sample analog to be good? Guys.
Is that when we said that it needs to be unbiased, consistent, and efficient?
Absolutely. The sample analog is an estimator of the true population parameter, right? And this estimator to be good, you have to satisfy, it has to satisfy all these three requirements. And we already discussed what they mean, and we showed two estimators, Y bar, Y16, and we talked about that last class. And Y bar we showed is unbiased, consistent, and efficient. Guys, we did it before, right? So, okay, so Y bar is an estimator for mu of Y, right? But then, okay, and that allows us to have some ideas about mu of Y, okay? It is in fact, Y bar is in fact the best possible estimator for mu of Y. Okay, so let me now explain hypothesis testing based on the following example. Let's assume that let's assume that you want to take a class of some of the professors, and before you take the class, you wonder what is the mean outcome in his class, and to have that information, you need to ask every student that this professor ever had about their results in his or her class, right? So you will have to do a lot of work, right? And it also can be very costly, right? So, okay, then what you can do is that go directly to the professor and ask, right? What is the average result in your class? Or to be better specified, I would ask, like, what is the average result in all of the classes that you have taught in this particular course? And he can say that average, the true mean of the results, which is like the true mean, right? Of the true mean of the results of from all the classes I have ever taught, he can say is mu of phi is, let's say, whatever, mu zero. Mu zero can be, let's say, then can say mu zero is 83, right, out of 100. Okay, so he says that, right? And but do you believe in that? That's the question, right? So he may be saying truth, he may be, or she may be lying, and you want to know, right? And you never know exactly, because you don't know the results of every student in this particular course that he has ever taught. So then this is not the fact, this is just whatever he said or she said. But for you, this is not a fact, this is just a hypothesis, which we call H null, the null hypothesis. This for you is null hypothesis. Guys, am I clear?
Yes. Yes.
And there can be 3 different alternatives. If the professor is right, then this will be true. But if he's not right, then mu of y can be less than mu zero, or mu of y can be greater than mu zero, sorry. Or mu of y can be different from mu zero, right? This we call left sided test. Guys, please turn off your microphone if I'm not, I already muted everyone, but this is right-sided test. Because you have greater, and this is like two-sided test. And before I told you guys that you can use y bar to test the hypothesis, right? But to do that, you need to calculate test statistic, which we already discussed before, and the test statistic has the following.
Can you move the screen a little bit up, please?
Yeah.
Wait, yeah.
The statistic is y bar minus mu zero divided by sigma of y bar. Guys, if you want to get more details about how we form test statistic and what the statistic is and stuff, please listen to my previous class recording. Right. Okay, this is the test statistic, right? And then, but then I said before that we started from the following assumption, right? This was that yi is IID normal with mean of mu of phi and standard deviation of sigma of phi, right? But then this implies that y bar is also IID normal. But what is the mean? Mean is the same, mu phi. But what is the standard deviation? That sigma of phi divided by square root of phi. And this is explained in the previous class. Now, guys, okay. So what do? You take a sample of certain number of students, you get y bar, you calculate y bar, you have y bar, you can also calculate sigma of y bar. The sigma of y bar is not known, this is the population parameter, but you can calculate standard deviation from your sample, right? Which we denote by S of phi bar. And this S of phi bar is an estimator for sigma of phi bar. So you can use this for instead of sigma of phi bar here. Okay, so let's say, and then when you get the number, let's say y bar. Let's say you took a sample of let's say n is n should be greater than 40 if you want to make a reasonable inference, at least 40. But okay, and I will say more about this later. Let's say y bar. Let's say you took a sample of size 40 and then you ask each individual in the sample, what was your score in this professor's class? And you simply calculate this, right? 40, right? And let's say this is 78, right? So this is clearly different from 83, right? But this is in absolute, like this difference is not in statistical sense, it is just an absolute difference, right? So this is different from that by 5, but doesn't mean that 78 is different from 83 in a statistical sense, and we are only interested in whether 78 is different from 83 in a statistical sense, and I will explain that in a minute. And let's say assume that sigma of y bar is, let's say 1.52, can be anything. Okay, if you don't know, if you do not want to make this assumption, then you can say that, okay, calculate this S of phi bar, and that's S of phi divided by square root of n. That will be, and you know how to calculate S of phi, right? And let's say this is whatever, let's say then 52, doesn't really, if you don't know that, okay. And what you can do is the calculate test statistic, right? And this will be what y bar, which is 78 minus hypothesized value, which is 83 from above, and then divided by 1.52, right? Note that I wrote this is sigma of phi, but if I gave you sigma of phi, then you would be dividing that by square root of n to obtain sigma of phi bar. So be very careful, guys, when you do stuff. And this is approximately, I have no idea. Let me calculate that. You can simply calculate it in Excel, but if you calculate it already.
Oh, Professor, can you scroll up a little bit?
Yeah, just give me a moment, please, so that I calculate that. -78 minus 83 divided by 1.52, that's minus 3.29 approximately.
Got it. Thank you.
And then you compare the absolute value of this test statistic to the critical value at a pre-specified significance level. Let's say we want to test our hypothesis by 95% confidence, which means 5% significance level. And we know that, and I gave you that in the table in the previous class, that the critical value, we call that Z critical. The critical value is for this 1.96. I will explain all of them in details, but for now, just it's not equal, right? And you see that this is greater. So, which means that reject H null, because it is greater than this critical value. You reject H null, that means that the professor was lying, because it's not 83 based on your sample. The average, the true mean result in his or her class is not 83. By 95% confidence, you are saying that based on the sample you took, right? It's different. So this was just an example, but we will have many more examples. And now let me tell you guys, there are three methods to test a hypothesis. One is using test statistic and the critical value. So, and if the absolute value of the test statistic is greater than the critical value, right, then reject H null. This is like when you have this situation. So I said before that the critical values, this is the critical value, which we call Z critical. This is small z, capital Z is on this x-axis, and this will be Z minus Z critical, right? Because this is a normal density which is symmetric, so it is 0. And in our example, Z critical equals 1.96, and we obtained that test statistic, the absolute value of the test statistic is minus 3.99 in absolute value in module, which is 3.29. So the 3.29 is here, that 3.29. So the area below, or you can say beyond the critical values, are known by rejection areas. Or rejection regions. Here we have 2 rejection regions. And we see that this 3-point test statistic falls in one of the rejection regions, so you reject H. Now that's one way to test the hypothesis. Another method is using p-value. I will explain what p-value is in a minute. So p-value is the probability that z is less than the sorry, right here. Z is less than a test statistic, which is phi bar in this case minus mu0 divided by sigma of phi bar, but note that sigma of phi bar is once again set sigma of I divided by square root of n, right? And but you have to put this in the less than okay, so it will be okay. Let me rewrite this. Not less than, you can write it like that. As okay, you can write this, and this you can say 2 times that. That's the p-value for two-sided test. But you can also say that p-value is, and I will explain all of that in detail. So don't worry if you don't get something right now. Probability that C is greater than the absolute value of y bar minus mu0 divided by sigma of y bar. So see, those are the same because for two-sided test, because here you have like this area and this area, right? Okay, and the same thing is here. So let me explain this on an example. On our example, we calculated that y bar is, what was y bar? Y bar was minus, not y bar, test statistic, guys. Test statistic was minus 3.29, right? So what is p-value? Remember that p-value is associated with the test statistic. Whereas the significance level alpha is associated with the critical value. Now let me draw this, which was in our case 1.96, right? Now, so let me draw a table, not table, sorry, but figure. Here we have, as I said, above C, and this is our normal distribution. And so guys, if you have questions, please let me know. And I said, okay, this is 1.96, and this is minus 1.96. The significance level will be Z area plus Z area. Okay, this is area 1, area 2. So the significance level, which we denote by alpha, alpha in this case equals area 1 plus area 2. But now, okay, then what's the p-value then? Okay, we obtained that the test statistic is minus 3.29. The absolute value is 3.29. Then the opposite here is minus 3.29, and the area above 3.29 and below minus 3.29, I will call this yellow. Area 1, I will call this yellow. Area 2, the p-value equals the sum of the two yellow areas. And can you guys tell me, is the p-value less than or equal or greater than the white areas significance level?
Yellow's greater?
Equal?
So guys, you are seeing, right? This, do you see my blue screen?
Mm-hmm. Less than?
Less than, because this white area includes these yellow areas, right?
Oh, yes.
Yes, sir.
Yeah, so the white areas include those. So the white areas are in our, the p-value is this yellow areas. But this is less than the significance level. Okay, you want me to be like very clear, and let me try that. That's less. So we pick the color. It's less than. Do you agree with this statement?
Yep.
Yes.
So that means this is a general thing. That means reject H now. But you, okay, significance
Professor,
level, yeah, okay, so
Could you
wait.
give us examples of all the scenarios?
Sorry?
Later, could you give us examples of the scenarios? All three of them?
So please, follow as much as you can. You'll get a lot of examples, but these are like very important. So, and of course you'll get examples. So significance level is 0.05, right? But you want to have a number here. Okay, from this picture I see that yellow areas are less than this white areas, but I want to have a number. Okay, here, because I want to have a number for this p-value, right? Then you need to use a table, or you can use Excel. Now let me, this is, I think is a good time to make use of the tables. You don't see my, you still see my blue screen, right?
Yes.
Yeah.
Yes.
Yes.
Okay.
Are you
now,
providing us with the Z table now?
yeah. So now I have to reshare another screen, and I will. Now you should be seeing the table. This is a standard normal table. That small z there is a specific value in that. In our case, that z is 3.29. And the capital Z is measured on this horizontal axis, and this phi symbol stands for, I mean, that what it means, right? So this phi symbol, that's a circle with a line in between. The phi of small z, that means the probability that capital Z is less than or equal than small z, right? And if you want to see what's the p-value in our example, then what you can do is that, let me share my screen again. Guys, okay, I'm very happy that I have so many students. So what would be p-value? These two areas are the same, right? So because this is a symmetric density, because of that area, yellow area 1 equals 0, area 2. So the p-value would be 2 times yellow area 1, right? Do you guys agree with me? And that's what I have here, but written in a formal way. Where was it? Here. Here I wrote it in a formal way, but you don't really need to know that. What you really need to know is that this p-value is 2 times the yellow area 1, right? And guys, do you agree with me?
Can you repeat that, please?
So p-value will be 2 times the yellow area 1, because yellow area 1 equals 0 area 2. So, but what is yellow area 1? This is 2 times probability that this capital Z is less than minus 3.29. And this is something that you can either take from Excel or whatever statistical software, or maybe you can use a table. But table is not very exact, but you can still use the table. This is 2 times probability that Z is less than 3.29. So this is a small z. Small z. Right? In that table, z's, small z's, are decomposed into 2 parts, minus 3.2 in this case and 9. And let me reshare the screen. So minus the first minus 3.2 is measured on this in this column, and this last decimal is measured on this horizontal part. So, and this table tells us the probabilities that capital C or a standard normal random variable C is less than specific value of your capital C or small z is in our case minus 3.29. So, okay, then minus 3.29 is not here at all. The first is minus 2.9 and 9. That's that's very like, this is the first that you see. It's like this. That table does not go beyond Z, so it's like the table stops here. Let's say here you have minus 2.99. That table stops there, and the table tells us that the probability that Z capital is less than minus 2.99 is already 0. Okay, then because probability that Z is less than minus 3.29, sorry, is clearly less than the probability Z is less than minus 2.99, this will be 0 as well. So, which means that we will have 2 times 0 here, and it is 0. So, okay, and then that's what you plug here.
Professor, I don't see your blue screen. Are you writing something?
Yes, yes. I will repeat. Now, do you see my blue screen?
Yes.
So what
No,
I said
not
is,
yet. Oh yeah, sorry.
Yes, we do.
so what I said is that this 2.99 is somewhere here, let's say here, right? And the table tells us the probability that C is less than minus 2.99 is 0 because, right, so now I have to reshare my screen again, but believe me, the table tells you Z, and but 3.29, the probability that Z is less than 3.29 is even less than probability Z is less than 2.9 minus 2.99, which is already 0. So probability Z less than minus 3.29 will clearly be 0 as well. So then you will have 2 times 0, which is 0. Sorry for the background noise, guys. I'm not sure what's going on, but some of my neighbors started something. So 2 times 0 is 0, right? And then that's what you plug here. And so 0 is less than 0.05. P-value, we obtained this 0, which is less than 0.05, which is the significance level at 5%.
Can you explain again how you figure out 0 from the other PDF, please?
Yes, now that is something I will share with you guys. Do you see the table?
Yes.
Yeah, we can always.
Yes.
So this table gives us probabilities that capital C is less than or equal small c. As I said, Z is decomposed in 2 parts, minus 2.9 in this case and 9, right? So, and that is, so you can combine Z with this 9 here, and that this number is the probability that capital C is less than minus 2.99, okay? And this is almost very close to 0, right? So because of that, I wrote approximately 0, right? But you can get exact number in Excel, and I will teach you that as well, maybe later, not today. Because of that, I wrote here 0 approximately, and this will give you approximately 0. And then you compare 2 times 0 because you are interested in 2 times 0 because 2 times that probability, and that's clearly 0. So p-value is 0, which is less than the significance level at 5%. So this means that we reject H now. That's another way. Of course, you get more and more examples, but clearly you will need to understand everything I write in this Flow document and the class slides as well. And clearly, as I said, you will get more examples later. There's another way to test the hypothesis, and it is by the third way to test the hypothesis is by using confidence interval for mu of phi. Mu y bar, but mu y bar is equal to mu phi, right?
Can I ask a question?
Yeah, sure.
In the previous example, where did you get 0.05?
But this is pre-specified. I said, so did remember in the last class I had 3 common ways of significance level? So it's three common significance levels: 5%, 1%, 5%, 10%. The critical value. Sorry, I said before we had 3 different critical values that correspond to 3 different significance levels. And we had 3 different critical values like 2.58, that was at 1% significance level, 1.96 that was at 5%, and 1.645 that was 10%. But this is pre-specified.
Oh, okay, thank you.
You specify that, or I specify it in your problems. And another way, this is the last method of testing the hypothesis, is using confidence interval. And the confidence interval for mu of phi has the following. For mu phi is we'll say confidence interval is how to write it in a understandable. Okay, let's say is n is greater than 120. I will say why is this important. And then we have 1% confidence interval. That's y bar minus c critical, which is in this case the general formula is this: bar divided by square root of n. Sorry, let's sigma phi bar sigma phi divided by square root of n and y bar plus c critical times sigma phi divided by square root of n. That's the confidence interval. If you don't know sigma phi, you can use S of phi. Okay, and z criticals, as I said, have 3 common values, which is 2.58, 1.96, and 1.64 and 5. This is depending on alpha. The significance level here is 1% or 0.01. Here alpha is 0.05 or 5% significance level, and here alpha is 0.10, which is a 10% significance level. And because of that, you get 3 different common confidence intervals depending on the critical values, right? And if mu 0, that's the hypothesized value, falls into the or within, you can say, the confidence interval, then we fail to reject the null hypothesis, right? Those are 3 different methods of testing the hypothesis. And now I will do a specific problem for you guys, and that will hopefully clarify a lot of stuff. Okay, now before I proceed, I have to, let me copy some exercise from our class slides, because I think that will be very useful. me copy this. You still see my blue screen, right?
Yes.
Yeah.
Now let's do this. Just checking, guys. Do you hear a noise from like my side?
There's a
Just a
pop-
tiny bit.
Just faint, just a little bit.
Background.
We're sorry.
And that is something I cannot really take care of because it's not me. Do you now see that I pasted something?
Yes.
Some examples.
Yes.
Good. Now let's do this. So here we will be testing some hypotheses, but it will be very, very similar to what we would be today. This average of two mean average grade of mean grade of three professors. So what do we have here is that we have some sports string and so they say that each bottle contains 140 milligrams of potassium. So that is noted on that bottle. Okay, and the thing is it really that amount? How would you specify the hypothesis here? So clearly, there is some true mean, right, of the potassium content in these bottles. Of course, you can cannot get like you cannot really examine all these bottles, and you cannot really know if the true mean potassium content is 140 or not, but the bottles say that. So then this 140 is the hypothesized value. So the thing is it really 140 or is it different from that? So the null hypothesis would be that the true mean of the potassium content is 140. This 140 is mu 0, right, from above. Guys, are you with me?
Yep.
Da.
Good, good. So now the alternative is can be either it's not 140, can be like then it's less than 140, more than 140. We will discuss them later, but now let's do this. And then the analysis of 20 bottles, which means that the sample size is 20, right, indicates that the mean is 139.4. That is what? That is Y bar. Okay. For two-tailed test, we already did this part A. Right, so that is already done. Now let's, assuming that we know the true standard deviation of each bottle, then we can say sigma of y equals 2 milligrams, and it is very important that we have this assumption that the population is normally distributed. I will say more about it later. And we now want to test the hypothesis, right? So we want to test this hypothesis, right? We can do it in three ways. First, we can calculate test statistic, right? Test statistic will be let me remind you the formula for that. This is y bar minus mu 0 divided by sigma of y bar. What is y bar in our case?
139.4.
Yes. What is mu 0?
140.
What about sigma of y bar?
2.
No, it's going.
Isn't sigma y bar going to be sigma y over square root of n?
So 2 divided by,
20.
so we are clear, right? Guys, are you with me? If you have any questions, don't hesitate to ask. And I need to calculate that now because I don't have it ready, unfortunately. So. I find Excel very handy for this kind of calculations.
Professor,
Yeah.
I think there's some software you could use, correct, to help you solve these type of questions. Will we be able to will you show us how to use that too, the software?
I will show everything, guys. I will show you everything you need to know. I mean, about in this course that I will teach you R, the basics of R, Excel, everything. So you can of course do it in R as well. So I will teach you some R, but not now. Am I clear? Now we need to understand these concepts, guys, and the examples. And so I got minus 1.34. Do you still see my blue screen?
Yes.
They say test this by no, what is it? Says it. What is the pre-specified significance level? 10%, guys, see, 10%. We know that that Z critical at 10% subscript 0.10 is what? And then we compare the absolute value of this test statistic to this, and we see it is less than that. So this means fail, to reject. H null. So instead, yes, based on my sample of 20 bottles, I find by 90% confidence that yes, the true the mean I got from the 20 bottles is not statistically significantly different from the true mean of 140. That's what I.
Professor, how did you get 1.1.9? What is it? 1.169.5?
That's the critical value at 10% significance level. And I will. So these three different commonly used critical values are something that we need to, you can memorize, but I will show the exact derivations now. So we have this situation. This is capital Z. Then we have normal density. And have this 1.64 and 5, and this is 10 minus 1.64 and 5, 5% significance level means that these areas, these white areas, add up to what? Add up to 0.05, and because these areas are equal, then you will have 0.025 on each side. And this 1.64 and 5 would be what? Probability can be found from this. Probability get capital C is less than small c, that is 0.025. Do this, and you will get set c equals minus 1.64 and 5. Right? But now, what about minus 1.345? That's below z, so minus 1.64 and 5. So this does minus one. Wait, what did I do? Does this minus 1.345 fall into rejection region?
No.
No. So that's why you fail to reject it. Are you with me, guys? That's why you reject it.
Yes.
Now, what would be p-value? P-value would be the area below minus 1.345 and the area above 1.34. So is p-value greater or less than the significance level here?
Greater.
Greater, right? What is the significance level? 0.10, right? Oh my God. This is 10%, so I should have here 0.05 cent, right? And this would be 0.05. Here it would be 0.05, and both would add up to 0.10, right? 10% significance level. But okay, this is 0.10, but the thing is, what is this? The p-value, if you want to calculate, that is 2 times probability z. Capital Z, or a standard random variable Z, is less than what? Guys?
Less than the y bar minus mu 0 divided by standard deviation of y bar.
That's exactly right, but you see the number, right? So you see the number.
0.34?
0.34 minus.
1.3.
Minus 1.
1.34?
Yeah,
Minus
yeah. I don't know where do you see 0. But I'm not sure, but I have it minus 1.34.
34.
Where do you see this probability?
Yellow?
Table 1 or Excel or some other statistical softwares?
Okay.
Yeah, true. Sorry, go ahead.
So we're supposed to look up negative 1.34 on the Z table, correct?
Yeah, true. But this needs to be decomposed, right? Minus 1.3 and 4, and then you can see. Now let me share a new screen. Where do I have? Do you now see my blue screen?
Yes.
So minus 1.3 is here, 4 is here. So that would be 2 times that would be the p-value, right? Guys, do you agree with me?
Yes.
So 0.0901 times 2.
0.1802.
0.090. What was it? I already forgot. 0.0901
01.
is, and that will be
0.1802.
Yeah.
and then okay, so that's 0.1602. Is it greater than 0.10?
It's
It should be
0.18.
18.1802.
Yeah, it should be 18.
Yeah, I am very bad in arithmetic, so
No,
18.
18.
18, okay. Are we okay right now?
You can rewrite it. It's kind of hard to.
So this is greater, right? Than 0.10. So then, so that means we reject or fail to reject. We reject if that's the general rule that p-value, if the p-value is less than alpha significance, but now it is not less, so we fail to reject. H null, which confirms the conclusion that we obtained from comparing the absolute value of the test statistic to the critical value. Am I clear?
Yep.
Professor,
Yes.
I just have one question. When you go to the Z chart, why did you go to 4?
Because minus 1.34 is decomposed in a very weird way, because the table is very weird. So it decomposes these numbers by 1.3 in this case and 4.
Oh, wait, where'd you get the 4 from?
Because it is part of 1.34. That's
Oh, you're just, okay, never mind. Okay.
yeah, that's the second decimal of the
Thank you.
test statistic, right?
Professor?
Yeah.
So we failed to reject because the p-value we got is less than which number?
No, we failed because it is greater. If it was less,
oh, okay.
Because if it was less, then we would reject it. What I said is reject if p-value is less, but we failed to reject because p-value is greater than significance level.
Okay, all right, thank you.
Professor, and
yeah.
Okay, never mind, I got it.
Okay, if you guys got it, the class is over.
Professor, can you show the text again, please?
Yeah. Which one?
The questions.
Yes.
Thank you.
Yeah. And we found p-value, so we did everything. So we finished this problem.
Professor, so is the alpha symbol, does that mean level of significance?
That is exactly what it means.
All right, and it's, all right, got it.
Professor, there's one thing in part C that I didn't understand. It's how you got the number minus 1,645.
That is the critical value at 10% significance level, which is you can either memorize or you can find it. And I gave you here how you find it. This is minus 1.64 and 5 is this Z here.
Okay, when you say memorize, what do you mean by what do you need to memorize?
First of all, don't memorize anything. but still, I mean, if you don't want to memorize, then this is how you do it. But there are some conventional stuff that everybody knows. So there are 3 different levels of significance, meaning alpha is 1%, or 0.01, alpha is 5% or 0.05, or alpha is 10% or 0.10, and they correspond to the critical values, and the critical value here is 2.58. That's what people memorize, but don't memorize anything because you can calculate that from here. This is 1.96 and this is critical value. CV stands for critical value. Here it's 1.645. But that's when n is large enough. So here n is greater than 120.
Okay, thank you. And just to make sure, is it negative or positive, or it doesn't matter?
Doesn't matter. It,
Okay.
it can be negative, it can be positive.
All right.
It matters where you, depending on the type of hypothesis you are testing. It can be one-sided, two-sided. So I will give you more details about that. But right now, please follow whatever we did. And we will have more details later.
All right, thanks.
So today's class is over. I will just
Professor?
answer. Yeah.
Can you just draw the symbol for alpha again? Because I just want to be sure that I know what it looks like.
What?
Like how
It's
how
like
would you
Sorry, can you please repeat it because I don't understand your question.
can you just show me how the alpha symbol looks like, please?
Ah, okay. Alpha looks like this.
Okay, got it. And that could sometimes be denoted as A, correct?
No, it is always alpha. That's the significance level.
Okay, got it. Thanks.
Professor, what about this 0.05 from where you got it?
Because 10% significance level for two-sided test means that you have 5% in each tail. 5% means 0.05 in this tail and 0.05 on that tail.
Okay, then.
I think I will continue what? So first let me save this. Some of you, I think Hassan, if Hassan is here, he asked the question.
Yeah, I'm still here.
Let me share my screen and let's do that problem. Let's see. So here, the question is, calculate the unemployment rate for college graduates. So they're asking, what's the probability that a person is unemployed with y equals 0, conditional that you are a college graduate? So that's y equals 1.
Hold on. Can you just repeat what you said? Like how you wrote it out?
Yeah, so probability that y equals 0 means that that's the probability that the person is unemployed, right?
Yeah, so it's unemployment rate for college graduates. Okay, I get it.
You got it, right?
Yeah, I just like, so depending on how you read the question, you could we could word the question
No, so
differently.
you have to read the question correctly.
Yeah, that was my issue.
I think they are very clear here. They're saying calculate the unemployment rate for those who are college graduates.
Right.
So
Okay.
the condition is here, a college graduate, whether you are a college graduate or not. Sorry, that's why, sorry, that should be X, right?
Yes.
College graduate.
Yeah.
And then
So
you proceed from there.
So I'm trying to help, like, when I'm reading this, I want to be able to know which comes first. Like, so I assume in the question it says unemployment rate 4. So because it says 4, we know that it's conditioned on something, correct?
So the thing is, so Hassan, I don't know, the thing is, to me, they sound very clear here. So it's like they're asking to see what's the unemployment rate for those who are college graduates.
Yeah.
So they are already college graduates.
Okay, yeah, I get it. Thank you.
Okay, so then let me stop recording, guys. That's the end of today's class. I will continue on Monday, and hopefully you'll be all here